Okay, let's talk about physical AI.
Knowledge enterprises use agentic AI to automate digital work.
Hello, I'm James, a digital human.
Industrial enterprises use physical AI to automate physical work. Physical AIs are models that can understand instructions and autonomously perform complex tasks in the real world.
Physical AI is set to be the focus of the coming years. At CES this year, Nvidia unveiled a groundbreaking advancement in this field, Cosmos.
Effectively, the world model of, as opposed to GPT, which is a language model. And this world model has to understand the language of the world. It has to understand physical dynamics, things like gravity and friction and inertia. It has to understand geometric and spatial relationships. It has to understand cause and effect.
Nvidia Cosmos is a platform of state-of-the-art generative world foundation models, advanced tokenizers, guardrails, and an accelerated data processing and curation pipeline built to accelerate the development of physical AI systems such as autonomous vehicles and robots. Let's look at the Cosmos paper NVIDIA released. So, the paper, they propose a pre-training and post-training approach for world foundation models. To build a pre-trained foundation model, they leverage a large-scale video training dataset to expose the model to a diverse set of visual experiences. To create a post-trained foundation model, they fine-tune the pre-trained model with a specialized physical environment.
It includes auto-regressive world foundation models, diffusion-based world foundation models, advanced tokenizers, and an Nvidia CUDA, an AI-accelerated data pipeline.
A diffusion model generates videos by gradually removing noise from a Gaussian noise video. An auto-regressive model generates videos piece by piece, conditioned on the past generations following a preset order. These are some of the components in the Cosmos platform. Video Curator is first component. Each video is divided into shots. Filtering steps identify dynamic, information-rich clips for training, which are then annotated using a VLM. Tokenizers convert raw visual data, like images and videos, into compact semantic tokens, making it easier to train large models and run them on limited resources. In the video tokenization pipeline, a video is encoded into smaller, efficient tokens, which are then used by a decoder to reconstruct the original video. The goal during training is to ensure that tokenized representation preserves as much visual information as possible. The video is first processed using a two-level wavelet transform, which groups the frames and downsamples them by a factor of 4 in space and time. This helps reduce redundant pixel information and compress the video into a more compact representation. The model uses the swish activation function, which is a smooth, nonlinear function to introduce nonlinearity into the model. Layer normalization is used to stabilize training. The encoder uses spatiotemporal convolution to capture the spatial information. The training strategy for the tokenizers alternates between many batches of images and videos at a preset frequency. In the first stage, the model is optimized using L1 loss, pixel-wise RGB difference, and perceptual loss based on VGG19 features. In the second stage, optical flow loss ensures temporal smoothness for video reconstructions, while Gram matrix loss enhances the sharpness of image reconstructions. Image tokenizers are trained at compression rates of 8 and 16, while video tokenizers are trained at 3 compression rates. For the evaluation, they use the MS COCO 2017 validation subset of 5,000 images and ImageNet-1 K validation subset of 50,000 images. For video tokenizer evaluation, there is not yet a standard benchmark for high resolution. They also introduced token bench dataset for this purpose. As mentioned earlier, for pre-trained foundation model, they used autoregressive transformer and diffusion transformer. Let's look at the architecture of the two briefly. The model processes an input video through the encoder of the tokenizer to obtain latent representations, which are subsequently perturbed with Gaussian noise. These representations are then transformed using a 3D patchification process. In the latent space, the architecture applies repeated blocks of self-attention, cross-attention, integrating input text, and feed-forward MLP layers, modulated by adaptive layer normalization, scale, shift gate for a given time step t. The decoder of tokenizer reconstructs the final video output from the refined latent representation. Let's look at architecture of autoregressive transformer. The pipeline begins by encoding input video through the encoder of Cosmos tokenizer to generate discrete tokens, which are transformed into learned embeddings. These embeddings are processed through repeated transformer blocks, each consisting of absolute positional embedding and 3D rope components that are flattened before entering the self-attention module. Each block also includes a cross-attention module that incorporates encoded text prompts processed via a T5 text encoder, followed by a two-layer MLP. Finally, the decoder of tokenizer reconstructs the video from the output tokens. The Cosmos tokenizer uses a lightweight encoder-decoder architecture as a result of aggressive compression. It sometimes leads to blurriness and visible artifacts in video generation, especially when only a few integers are used to represent a rich video through discrete tokenization. They solved it using the diffusion decoder design for further enhancements. During training, each input video is tokenized twice, one through the target discrete tokenizer and the other through a less constrained continuous tokenizer. The discrete token video is used as the conditional input to the diffusion denoiser. During inference, the output video token from a Cosmos autoregressive model is conditionally inputted to the denoiser. For the safe use of their WFMs, they develop a comprehensive guardrail system. It consists of two stages, the pre-guard stage and the post-guard stage. The pre-guard stage leverages IGES and a keyword list to block harmful prompts. The post-guard stage blocks harmful visual outputs using a video content safety classifier and a face blur filter. The tech report is huge. I think we covered a lot of topics from it, but let's wrap it up here. The Cosmos platform is simply outstanding and shows a new direction in physical AI. The framework is open-sourced and ready to use. I have added the link in description for the framework. Let's quickly go over the platform with a quick demo. That's all from our side. Hope you enjoyed the video. Don't forget to like and subscribe and see you in the next video.